Hey, how are you? Good, thank you. Oh. How are you? This semester keeps being fast. Although the summer seems like it's going to be as busy. Yeah.
It would be nice to not have classes.
Yeah. More reading, more time to read.
All right, let's start. So I'll make some announcements today and about the second midterm, and then we'll review IDs. So the midterm is it's Tuesday, I believe. And then, so the format will be same as the midterm one, and it is non-cumulative, and yeah, calculator is needed this time, or a calculator app on your phone with an explanation feature in it. So I mean, by a calculator, I meant more of a calculator with an explanation feature in it. Does that make sense? Or logs. And then you should be able to use that functions, these functions on your calculator. If you have troubles with figuring that out, I'm happy to talk more about it in my office hours. So don't feel treated by these features, and I can guide you through it if you need help. And there is cheat sheet contest in there, so you can submit your cheat sheet with the exam, and then it will be just as the midterm one. Any questions about the midterm 2? Nope. All right. Before starting, is there anyone who didn't get the homework back yet? Oh, okay.
I'm sorry. My phone said didn't break for some reason.
Okay.
I just
Sure. After. All right. Yep. Then let's start with the instrumental variables. So instrumental variables motivation is to resolve unobserved heterogeneity issues, meaning that correlation between T and Y is not exactly effect. So I'll give you an example. So if you're interested in looking at the relationship between parental SES or socioeconomic status, which is typically measured with household income, father's education and mother's education, and father's occupational prestige. And let's say so far at this point, parental SES is measured without mother's occupational prestige score. I'll explain why this is a problem along the section. Basically, what we're interested in is this is measured with various the combination of various characteristics such as household income, parents' education and father's occupational characteristics. Good. Any questions? No. And then you are interested in looking at the relationship between parental SES and child age. And the problem here is there are other family characteristics. For example, grandparents. SES could affect parental SES and child's age. Good. Any questions so far? So this is a problem, right? If these variables are unobserved. So that way, you cannot really figure out the causal effect of parental SES on child's age. So to deal with this problem, the IV strategy is to figure out. So basically, what it does is divide covariance between this instrument variable, say economic status at parents' marriage. I'm assuming that this is the children are living in the household with double or dual parents, not a single mother or not a single father. Good. And let's say this is measured with unemployment rate, okay, at the time. So what it does here is to divide covariance between this instrument variable and y, child's wage, by covariance of C and T. This becomes AB divided by A, and it becomes B. Why is that? Z and Y, right? To calculate the covariance between Z and Y, you should look at open paths, right? So let's start from Z to Y to get to Y. There is this path, right? This is a path. Economic status, parental SES, child's age. This is an open path, as you may know from path models lectures. And there is another path, economic status, parental SES, other family characteristics, and child's age. It is a path that is closed because it's a collider. In this case, it's a collider that is not controlled. Good. So you're basically taking advantage of parental SES being a collider in the specific path. And that's how IV resolves a concern of unobserved confounding variables. That's the IV's strategy. Good. Any questions so far? Nope.
I have a question.
Mm-hmm.
We assume that errors always divert to parental SES, but maybe there is some association from parental SES to all of them.
Oh, what?
There are some errors, some association from parental SES to the all of them.
This one?
Yeah.
Oh yeah,
The opposite
it could
of-
mostly certainly be possible,
Yes,
but
instrumental part may not work out.
right, yeah. But let's say this is true.
Okay.
And then yeah, we can move on from that. But yeah, if this is the case, you don't really need an IV, right? Because it is an indirect effect, right? So so there could be some complications. Obviously, this is a simple, straightforward example, but yeah, this is open to some complications, of course. Good. Any questions? So based on this insight, walled estimator of IE is constructed. This is noted as beta hat IV, and covariance of Z and Y divided by covariance of Z and T, right? And with some calculation, we can get this one. Because B here is covariance of C, oh sorry, T and Y. So I mean, sorry. So just without complicating it too much, I'll just say this is divided by dividing covariance Z and Y by the covariance of Z and T, and then this is the true beta, which what we saw from the previous example, and some remaining covariance between Z and EY, meaning that EY. So if there is remaining covariance between Z and Y, there would be this kind of pattern. Good. This is just an example. Z does not necessarily have to cause Y. It can look like that as well. So as long as there is covariance between Z and Y remaining, net of this, the indirect relationship through P, it'll be different from B. The beta estimate will be different from B. So we are assuming that this is 0. Basically. I'll cover more of that assumption later, but we will assume that. So that's why the hat ID is biased slightly, not slightly, biased but consistent. As sample size goes up, it'll be really close to the true beta. And variance of IV estimator is noted as this one. All right. Obviously, we don't know sigma for sure, so we are estimating it. So this is error terms variance, right? This is same as variance of error terms. Oh, sorry. Or estimated variance consistent. Right? So this is only applied if n is large enough. So, reminder, as a reminder, standard error squared, or variance of OLS estimator, was squared in variance what would be the difference? There is variance of z component right here, and variance of t is now covariance of z and t squared. There's differences, right? Does that make sense? Yeah. So that's why the standard of the Wald estimator is larger than the OLS, because let's say T and Z are standardized. That means that variance of Z is 1. Right? And variance of T is 1. We can easily standardize up here, right? So that way, so if so, variance of the IV estimator becomes this one. Right. So now the only differences here is variance of T and covariance of Z. Right? But from what we saw here, variance of T is here 1. And covariance of Z and T becomes correlation of Z and T if both of the variables are standardized. Right? By definition, correlation cannot be larger than 1. So therefore, unless Z and T are exactly have the correlation of 1, then the standard error of the Wald estimator is larger than the OLS. Good. Any questions so far? Any questions? And so I'll give you an example of a regression. Child's wage is rental SES plus E and is equal to 100. And we are using Z on status and marriage, parents' marriage, as an instrumental variable. All right. So, based on this covariance matrix, you should be able to calculate the beta 1 hat. Or estimate beta 1 hat. You can use two strategies, right? The first one is OLS estimation, and the second one is IV estimation. I'll give you the covariance matrix. Econ status, Z, and rental SES, T, and child's wage, and Y. This means Y. And covariance matrix shows us that they're all standardized now. And this one, the covariance matrix looks like that. Good. So if you use OLS estimator, that means that you are calculating covariance between P and Y divided by variance of T. That's the definition of OLS estimator, right? And covariance of P and Y was 0.4 as given, and variance of T is 1. Therefore, OLS estimator would be 0.4. This is pretty straightforward at this point, right? And let's calculate the standard error. So to calculate that, you should know estimated variance of E, right? That's where standard error estimation starts. Right? So to calculate the estimated variance of errors, you should start from this one. So, and then you throw both sides into the operator of variance. Variance operator. Variance of child's wage, let's just say Y now. Child's wage, or Y, is variance of beta 1 hat multiplied by T, rental status, and E. This is, if you decompose it, then it becomes variance beta 1 hat squared, variance of T, variance of E, and beta 1 hat multiplied by covariance. Oh, sorry. To be exact, it becomes now OLS because you started from the OLS estimator. OLS covariance of T and E. Good. Yep. All right. Since in the OLS framework, T and E are assumed to be 0, regardless of whether this is true or not. Right. So that's why it becomes 0.
That variance of E plus, what is that in front of?
This one?
To the right,
This one?
to the right, right there, what is that?
Oh, 2 multiplied by beta OLS.
Is it-
And so that's why, can I erase that a little bit? So therefore, 1 multiplied by 0.4 squared, because beta OLS was 0.4, okay? Multiplied by 1, and variance of E estimated. Good. And therefore, variance of E estimated variance of E is 0.16, or no, 0.84 actually. If you calculate that, you would get the number, right? And therefore, beta OLS was variance of E estimated divided by N variance of T, right? That was the formula, right? And square root of 0.84 100. And if you calculate that, you would get 0.0917. Good. Almost 0.1. So far it should be straightforward, right? Because that's what we have learned in OLS or 361, right? And we repeated that in 362. But in the IB estimation, the formula is different. This is 0.5 divided by 0.7. So if you calculate that, you would get this number. These numbers were given in the covariance matrix, right? Good. Oops. And if you want to calculate the standard error of the ID estimator, you should also start from here, right? Because you want to get the estimated variance of E. Variance of Y here is beta IB squared T Oops, sorry. Not. I was getting ahead of myself. But variance of beta IV hat multiplied by t plus e. Right? But then, so the problem of following this path is that if you decompose it, then you would have variance, covariance of T and E, right? This part. If you follow exactly the logic of OLS. But in the OLS framework, it was assumed to be 0. But, so I'll decompose it, just like the OLS. First. To IV covariance, right? But in the IV framework, covariance between T and E is not assumed to be 0. That's the reason why you want to use IV estimator in the first place. Right? Good. Any questions so far? So this way, following this path, you won't get the variance of the estimated variance of. Good. So what you can do here is subtracting this one to leave E alone. And then you can start do the same operator thing. Variance operate IV, sorry, IV T, variance of E. And that way, variance of Y plus IV squared, variance of log T, and 2 beta IV covariance of Y and T, and that becomes estimated variance of E. Technically, there should be this one as well, but good. So as we, according to the covariance matrix, you can plug in the numbers, relevant numbers, covariance between Y and T was 0.4, right? And there you have it. You can have the estimated variance of E. If you calculate the number, it should be similar to this one. Any questions so far? Nope. All right. And now you are plugging in this estimated error in the formula of IV standard error formula. It was variance of E estimated, variance of Z, and multiplied by covariance between C and T squared. As we saw, this was 0.9388, and this is 1, and this is 100, and from the covariance matrix, we got this number. Therefore, the standard error is 0. Oh, sorry about that. There should be squares. And this number is actually this one. All right. Good. So notice that standard errors from the OLS estimation and IB estimation, and the IB estimation is vastly different. Standard error for the IB estimation was larger, definitely larger, right? It used to be 0.1, but 0.09, I would say, yeah, 0.09, but it's now 0.13686. I mean, not sure it's vastly different, but still larger. Good. Does it make sense so far? Okay. And let's discuss before moving on to the assumption thing. So this is the basically you can calculate the standard error and the beta coefficient of IB estimators. But in Stata, actually you can do that as well. But the most popular estimation method is two-stage least squares estimation, which is basically conducting the which basically conducts the OLS regression of T on Z and that of Y on the predicted one T. And this is supposed to yield the same results for the beta coefficient and the standard error, but it has some advantages that we don't cover in this class. So just note that there are two popular methods of IB estimation, and they would yield the same results. But 2SLS has some advantage over log estimator. So I would say people typically adopt the 2SLS estimation. Good. Any questions so far? Let's talk about assumptions. Z is an instrument for T if covariance between Z and T is not 0, which is relevance criterion. And the second assumption is covariance between Z and EY is 0, which is called exclusion criterion. Okay. So I'll give you some examples. All right. So right, and wall estimator is covariance between C and Y divided by covariance between C and T, right? So the mechanism here is dividing AB by A. But if A is 0, then it becomes infinite or undefined. Like, oh, if this is 0, you're dividing some number by 0, right? So the estimate will be undefined. Good. So that's why relevance criterion is needed. It can easily testable. It can be easily. It is easily testable by looking at covariance between C and T. If they have strong correlation, they have a correlation, and then relevance criteria is satisfied. But a stronger assumption is actually not just 0, not just covariance between Z and T is not just should not be non-zero, or should not be 0, but they have to have a stronger or strong correlation. I'll explain why. So we're talking about this one, strong correlation between C and T. So this is related to relevance criterion, but we need a strong relevance, not just a relevance. So the standard error here looks like this one. As we saw earlier, right? But then, if covariance between C and T is too low, then standard error blows up. So the standard errors will be extremely large if the correlation is too low. Okay. And that's one effect of one consequence of weak relevance. And the second one is actually about bias in the beta estimator as well. So let's say we have U2, which is unobserved as well. That is correlated with both C and Y. And let's say C and D is extremely low. They're really small. All right. But then in OLS framework, it wouldn't change the results so much, right? So we don't have to care about it. For example, if this is 0.1 and this is 0.1, we don't really have to care about so much about that, right? The bias is not really high. But in the IB framework, covariance between C and Y, covariance between C and T, A here, AB plus C, right? C and Y, this path is open, but this path is also open. So this becomes B plus CD divided by A. But let's say we have all C 0.1, B 0.1, A 0.1. They're all 0.1, which is pretty fun. So in that case, in the OLS framework, A is not divided, right? So the bias will be 0.01. Right? But in that case, bias will be 0.1, which can be relevant. Let's say A is 0.01. Then. If that's the case, the bias will be larger. Does that make sense? Yeah. So a weak relevance might lead to bias in the beta estimator, even if this confounding effect is not so strong. Okay. So that's two consequences of weak relevance. On the other hand, Z should not be too strongly correlated to exclude the possibility that the unobserved variables are correlated with Z as well. So let's say Z and T are basically the same variable, right? If so, you must be related to this one as well. In that case, exclusion criterion here is violated. Does that make sense? So Z should be strongly correlated with T, but it should not be too strongly correlated. Good. All right. And let's talk more about exclusion criteria. So there are three types of exclusion violation. Again, exclusion violation means covariance between Z and EY is not zero. Exclusion violation means that. So instrument and Y is correlated somehow, net of the direct indirect relationship between Z and Y through T. Good. Before going over more of that, before going over types of exclusion violation, exclusion violation is not testable by controlling for T. There are some bypasses to test that assumption, but it's out of the range of the class. But the sure thing here is that to look at the relationship, the direct relationship between Z and Y, you cannot control for t to test that. Somehow you're thinking that, oh, to look at this direct path, I can control for t and then see what happens with this coefficient to test as if they are related or not. Good. But what is the problem here? What would be the problem? Controlling t would lead to, yeah. Yes, this is conditioning on the life. So that way, z and y's, even if there is no relationship between the covariance between z and y is 0, and not even if they are covariance of between the two variables is 0, you can have some relationship in your data if you control for t. So you cannot observe whether z and whether exclusion criterion is satisfied or not by controlling for t. Does that make sense? Yeah. Good. And let's talk about 3 types of exclusion violations. The first one here is there is direct effect of z on y. Okay. Covariance between z and y divided by covariance of z and t will be AB plus c divided by a, which won't be the or the true beta. Good. No. So, if there is a direct relationship between z and y, direct effect of z on y, exclusion criterion is violated. Therefore, the true beta cannot be identified. Good. And the second one here confounding of z and y. Okay. In that case, z and the result would look like that. Good. Any questions? Nope. All right. And the third one is actually a slightly tricky one, which is selective attrition. So in that case, I wouldn't use the math because it can be a little bit complicated, but it'll be just as if controlling for you are controlling for t partially. If you control for the descendant of t, it'll be just like partially controlling for t. Good. And therefore, you are conditioning on a collider. So there would be some relationship between C and U. Yeah.
So for the first and second scenario,
If
if we presumably observe, you can observe the U2,
Yeah,
And-
then you can control for U2, and that's fine.
and that D could be like valid IV.
D here?
Z.
Oh,
Sorry.
C.
Z
Oh,
can
okay.
be like a valid ID.
Sure.
Maybe.
yeah.
If we control like appropriately U2.
If this is observable, therefore controllable, then you can control for it. Then you can do that. Yeah,
And-
you can use that. You can use C as an instrument.
So for practical analysis, how do we do that with 2SLS estimation?
Oh, like what do you mean?
I mean, so 2SLS.
Oh, IV reg 2SLS.
Yeah.
And so Y variable and T variable and U2 where T is Z. T is affected by Z. I'll explain the command like in a minute,
Just
but it basically is just controlling for U2.
Just including the U2 at the second stage, not at first stage.
No, yeah.
Thank you.
Mm-hmm. Because so yeah, I don't. So basically, to without complicating things too much, so the 2SLS is basically conducting the more or less regression of T on Z and that of Y on the predicted T. And here you are adding a control variable. Please note that covariance between Z and EY being 0 does not mean Z have to cause Y via T. What I mean here is that, for example, let's say you have this DAG. Right? So here, covariance between Z and Y would be if this is ABC. CAB, right? Divided by covariance of Z and T is CA. And therefore it becomes B. So Z does not have to cause Y through T, actually. Even if this is unobserved, you are just fine. U2 is unobserved, you are just fine, right? Okay. So Z does not necessarily have to cause Y through T. Okay. Of course, in real research, this is really hard to find. This kind of situation is really hard to find because instrument tends to be sort of a random numbers or something like that. I mean, there are like some IB. There are some studies that are using IB to that could be interpreted as using this type of DAG, but it's typically really vulnerable. They're really vulnerable for counter arguments, honestly. So about like the DAG per se. Anyways. Any questions so far? All right. Then let's take 5, and we can cover measurement error after, and mistake as well.
I learned better.
Oh, really? Okay. Yeah.
Yeah. So like if we were to get like that's like I would have to rewrite everything. So that's just how I learned that.
Makes sense.
The speed, yeah. I don't want to miss anything.
Mm-hmm.
Maybe someone just thought it was
All right. Let's start again. So measurement error is an important issue. I mean, more important in certain fields. But anyways, so here, the key takeaway here is that IV can be a solution or a solution to measurement error, right? But before that, let me talk a little bit about mathematical notations of measurement error. So let's say we have these equations, right? So far, we have assumed that x asterisk, or the latent tendency of certain characteristic, is perfectly measured by x. For example, let's say parental SES is measured perfectly. It reflects someone's class background perfectly. We have assumed that so far. Good. But remember, from the previous example I gave you, let's say we omitted mother's occupational background, occupational prestige score, for example, and that could be a source of measurement error, right? Or a more straightforward example would be that let's say we are measuring students' reading ability, right? And then we are asking a series of questions to measure that, right? But the questions may not measure students' reading ability perfectly. It could be an insufficient measure, right? Does that make sense? Yeah. So even though, in that example, even though some students' latent reading ability is high, they could be sick, or they could be in a bad condition or something like that in that exam. So therefore, they have relatively lower score. Does it make sense? So far, yeah, basically. So this is noted as this measurement equation of x being x asterisk plus v, the measurement error. Good. So the observed x outcome, the reading score in that exam, in a specific exam, is the combination of students' reading ability or latent reading ability, the true ability, plus some measurement error. And the structure equation is that we are actually interested in the relationship between y and x asterisk, or the real students' reading ability, or which is latent and not observed. And here, we are assuming that there is no homogeneity between these two. So we are not looking at possible confounders or something. We're just focused on measurement error. Okay. Not confounders or anything. Good. So far here. And this one means that basically it's saying that measurement error is not related to anything. It's just random noise. Right? Someone could be sick. Someone could be in a bad condition or something, or in a better condition for whatever reason that is not really related to the outcome or the X level per se, the observed outcome, observed X per se. Good. Any questions so far? Nope. All right, good. Yeah. So in that case, beta OLS here is covariance between X and Y divided by variance of X. So note that X asterisk is latent or unobserved, right? So what we can do here is just run the regression of X and Y. Right? Good. So it'll be like if you combine these two equations, you would have the regression equation, right? It can be, it is same as X, no, X is X asterisk plus measurement error, right? And Y. That's why, right? A is omitted because it does not matter in covariance operator because it's a constant, right? And variance of X is variance of X plus measurement error. So, so we are looking at yeah, I'll just decompose it. This is covariance between X asterisk, comma B X asterisk plus covariance between V and BX asterisk plus covariance between X asterisk and EY and covariance between V and EY. So basically you are distributing each component in that part into the right part. Good. And as you can see from the assumptions here, they're all zeros. Good. Any questions? Nope. All right. And this is same as B multiplied by variance of X asterisk and variance of X asterisk plus measurement here. Good. And this part is called attenuation factor or reliability of measurements. Okay. So if this was, say, 0.7, then beta OLS hat is 0.7 of the true beta. Good. So that's why it's called attenuation factor. So if the problem set question says, oh, what if the beta OLS estimate is 2 and then reliability is 0.7, then what would be the true beta? Then you should be able to say 2 true beta 0.7. So beta should be 2 divided by 0.7, whatever number is. And this is also called measurement reliability because it is same as variance of x asterisk divided by variance of x. So the difference is basically the measurement error part right there. Okay. So if measurement error goes up, measurement error's variance goes up, then it would lead to the decrease of that measure, this part. Right? So that's why it's called measurement reliability, meaning that there are more measurement error, therefore reliability is low. Okay. Any questions?
Could you explain the equation, the covariance x asterisk?
This one?
Yeah, this one too.
So you are basically distributing each part to the segment. So that's how you can get the numerator. Good. So let me explain that with path models. So you should so far we have assumed standardized variables in path models, right? So the problem here is that we may write path rules for unstandardized variables as well, because x asterisk has no known scale because it's a latent variable. Does that make sense? It's a latent tendency in reading ability or something like that, so it has no scale, right? So meaning that we do not know the variance of or the scale of x asterisk without arbitrarily like fixing it. So the new rule for unstandardized variables is that you have to multiply the causal roots variance to the usual path coefficients products for unstandardized variables. I'll explain what I mean with an example. Right. Covariance of x and y here is, according to Wright's path rules, you should sum product all the open paths coefficients, right? Beta B plus AC. Right. This is for the path of this one, and this is path for X, Z, and Y. Right. But now you have to multiply the causal roots variance. So it means variance of X multiplied by B and variance of Z multiplied by AC. Does that make sense so far? Any questions? Am I making any sense? Because this is the causal root right here. Z starts the causality, even though this is not the starting point of the path. The causal root does not mean that it's a starting point of the path, right? It's causality starts from Z, basically. So that's why you want to multiply Z right there. This is the right path rules or unstandardized variables. Now let's multiply that or apply that rule to measurement error. So here, oops. So these equations say that this relationship, this stack, right? Because y asterisk causes y with the coefficient of b right there. And then x is the combination of x asterisk and b. And the path coefficients should be 1 and 1 because there is no coefficients multiplied. Good. In that case, covariance of x and y here is variance of x asterisk and good. Any questions? This is what we saw in the equation part. Right? In the numerator of the OLS that we just calculated. Any questions? Nope. Because, you know, x asterisk is the causal root of the path from x to y, right? So you have to multiply variance of x asterisk. Good, yeah. All right. And let's expand this case with the not sure if I want to cover much about it, but let's say we have this control here. B1x1, B2x2, x asterisk y. And covariance between x2 asterisk and EY is 0. Also, x1 is x1 asterisk, meaning that there's no measurement error x in x1. And x2 here is x2 asterisk plus b2. And so covariance between x2, b is 0, and covariance between b2 and y is 0. And there's no need to worry about this because there's no measurement error. All right. So what we're interested in here is the identification of B1 when x2 is confounding, x2 asterisk is confounding the relationship between x1 and xy. And there is x2 and b2. All right. So if there is a measurement error in x2, what would happen to x1's beta coefficient? That's the question. Good. Before calculating this one, let's talk about this new rule of note that covariance between y and let's just use this one. Covariance between y and x1 given x2 or conditioning on x2 is basically this one. x2 squared. So far, so for standardized variables, this one what used to be x1 and x2, covariance between y and x2. But now for unstandardized variables, you are adding this denominator. Right? That's the new rule here. So if x2 is standardized, it would be 1. Right? So it'll be exactly same as this one. But if this is not 1, then there should be some differences. All right, so in that case, now that we know this one, beta 1 OLS is basically covariance, or let's use that definition. Covariance between y and x1 given x2 by variance of x1 given x2. Right? This is same as covariance between x1 and x1 given x2, right? To make it compatible with this notation. So if you apply that rule there, then you will get covariance of xy, x1y, minus covariance. I'll use the notations above. Sorry, they're same, but covariance of y and x1 minus covariance of x1 and x2, covariance of y and x2 divided by variance of x2. That's the numerator part. In the denominator part is now variance of x1 and x, or covariance of x1 and x1, or variance of x1, and x1 and x2, x1 and x2 divided by good. So it used to be 1, right? It used to be 1, and therefore, if you control for x2, then you would have gotten the b, right? But this is x2 is subject to measurement error, meaning that this is variance of x2 asterisk plus v2. So if v2 goes higher, then the denominator gets lower. Does that make sense? So the verbal result here is that if there is measurement error in x2, it'll be just like there is remaining confounding relationship as if with the same sign of as when you did not control for x2. Does that make sense? Questions? So if you find it really complicated, I would suggest you can basically memorize like the key takeaway. If there is a measurement error in x2, then it'll be just like there would be a confounding relationship remaining even if you control for x2, because there is some latent x2 asterisk effectively on. So that's the key takeaway. Good. In a way, you're only partially controlling for x2. Good. Yeah.
Can you repeat what happens after V2 gets higher?
Oh, this one?
Yeah.
V2 gets higher, then it's supposed to be, so let's say, so the true B is identified when it's just one, or when it's just a variance of x. There's measurement error 0. Right? So this is, let's say B is identified when V2 is 0. If V2 gets higher, variance of V2 gets higher, then the denominator gets smaller. And the results should be different. By, like, so it'll be accentuating this part, right? So the confounders, the confounding relationship will be still remain. Does that make sense? Yeah, okay. And IV is a solution to measurement error, actually. Z, Y, X. This is 1. Right. A, B. So covariance of Z and Y divided by covariance of Z and T is basically covariance of Z to Y here is, if the variables are not standardized, it means variance of Z, A, B, right? Because this is the causal root of that path. Does that make sense? And Z and T, oh, sorry, Z and X now. X here is variance of Z 1A. Because let's say A1. The causal root is Z here, right? So you're multiplying variance of Z. But you should go A1 to get to the X variable, to get the correlation, covariance between Z and X. So that's why This is B. And it implies that IB is robust to standard measurement error in the treatment, as long as you are using Z as an instrument for it. And there is this multiple indicator situation where, so let's say we have two items to measure, so relationship or a variable. All right. Good. And so you are using Z, another measurement item for X asterisk, as an instrument for X, and vice versa. Good. So in this case, covariance of Z and Y divided by covariance of Z and X here is variance of X asterisk 1B multiplied by variance of X asterisk 1 by 1. I'll go more slowly. To get the Z and Y, the covariance of between Z and Y, you should go from here to here, right? This is Z, X asterisk, and Y. Right? And this is 1B. And you are multiplying 1 and B, the path coefficients, but the causal root here is X asterisk. So that's why you are multiplying variance of X asterisk. And by the same logic, you can get the covariance of Z and X. Okay. So in this situation, using Z as an IV for the measured variable X is helpful. It's robust to measurement error in X variable. Good. Any questions? Right. Let's look at data real quick. We don't have a lot of time, so I'll just explain what's going on here. This is the data, Angrist and Kruger's data. Do you happen to know Alan Kruger? Do you know who he is? No. Okay, yeah, he was a prominent economist who basically started the natural experimental method to say looking at minimum wages effect on employment and wages and stuff like that. So it's basically he started the whole methodological design to really look at how the impact of minimum wage laws on people's lives and stuff like that. And he used to work for the Obama administration for the first time, actually. So he was very prominent and stuff like that. But I heard that he committed suicide a month ago and passed away at the age of 58. So yeah, he recently lost prominent economist, really important figure in methodology, which is. Anyways, I just wanted to mention that because he was a really an important influential person in the Canadian. I really work for making the actual impacts by using technologies, stuff like that. So, yeah. Anyways, so he was looking. Angus and Kruger were looking at does compulsory school attendance affect school and earnings? So basically, they said that they were thinking that their research design was that being born in the first quarter somehow makes them, like with the laws and stuff like that, somehow increases the years of schooling, and that increases wages. Does that make sense? So Y was wage, and he was schooling, and he was being born in the first quarter. That's because actually, like, the law basically mandates the students that they have to stay in school until the either 16th or 17th birthdays. So that's why being born in the first quarter meant that you are basically starting older. Yeah, and then that increased like years of school. Does that make sense? Yeah. All right. To compare the results, let's run the OLS regression. So as you can see, education years is positively related to log of weekly wages. And so the T here is that P is that education years, but we are using Z to account for other to deal with this possible confounding relationship between T and P. Okay. But you don't want to include the Z in this regression equation, right? Because you don't want to control for. That means that if you include Z in the regression equation and then get the coefficient, it means that you are controlling for T to get the relationship between Z and Y, which is not okay, right? Because you're making a confounding relationship. So that's why you don't want to include Z in this equation. And the command here, let's look at instrumental variables method now. The command here is IB regress to SLS, and Y variable, and the T variable, and this is Z. Let's look at that. So it'll show you two tables. The first one is the first stage regressions, meaning that it is regression of T on Z. It looks the relationship between the two. Okay. As you can see, R squared is really low, meaning that even though it's significant, it's statistically significant, but R squared is really low, meaning that the instrument is really weak in a sense. The relevance is really weak. Good. And means that being in the first quarter is associated with lower level of schooling. Did I explain that being born in the first quarter increases your school year? It's actually the opposite. Yeah, because like the school starts in September, you have to stay in school by the 17th birthday. So that's why. And if you look at the second table here, education is positively associated with wage. So it means that A was 0.1, right? And AB here, and B estimated in the second table is 0.1, right? And the AB was 0.01. Good. So covariance between Z and Y must be -0.01. And then you are dividing it by covariance by CAT, which is -0.1. So that's how you can get 0.1 for the beta estimate. Good. And so the coefficient changes not very much, right? So they're arguing that this is a good sign. Actually, the compounder relationship was not too strong. If you assume that, I mean, there are some coefficient changes, but not too much, I guess. So what they're arguing is basically that the confounding relationship is not too strong if you're satisfied with the ID assumptions. Notice the standard error changes, actually. It used to be 0.0003, right? But here is now 0.023, which has been increased a lot. But still, it's significant, right? So it doesn't warrant too much concern in that sense, because it's still significant. Any questions about that? Nope. All right. So the second practice is the same thing, but with multiple instrumental variables. The logic is pretty much the same. So it's now not just Z, but a set of Z's. All right. Any questions? Great. Then I will see you tomorrow in lecture. A, B, yeah. Yeah, right, yeah. Yes, by the estimation. By, according to the estimation. Yeah, results. But then, like, you wouldn't inversely like guess top coefficients based on all that, because I mean, you can, like, it's always guessing, like, right? Guessing, like, estimating means guessing the path coefficients that based on our results, right? There is all. So what I mean here is basically it is always subject to sampling errors and some sort of violations in the error, violations in the assumptions of or ID estimation and stuff like that. So I would trust it as the final result of like the truth or something like that. There is always sampling error, violation of error assumptions and stuff like that.
You mean the results of the covariance?
Right, yeah.
Mm-hmm.